All right, here we go. Bearings. This is kind of like the bonus topic that I feel I need to cover. I've had many questions from students about bearings, and I just assumed that this was something that was a prior learning activity that you've done, and clearly I'm wrong. So I'm going to go ahead and do a deep dive now on what bearings are. And solve a few problems with them. Not too much for you to do here. Just one question I think that you should try. Well, there's maybe more than one to try, depending on how comfortable you feel with it. But what I've done here to get started is I've presented a screen capture from our syllabus, and the main part I want you to consider is the part I've highlighted here, which says contexts may include use of bearings. What does that mean? It means within the scope of a worded problem, there may be a reference to bearing. It won't be specifically tested, but you won't be able to answer the question appropriately or to the fullest extent that it could be unless you understand and can use bearings effectively. So that's why I want to do what we're doing right here. Okay. Bearing, the basic principle is this. If you're given a direction, if I said I want you to turn 10 degrees to the right, well, that's pretty straightforward. You understand what is involved with that, or turn about face, which is 180 degrees. All very clear. But a lot of directions are referred to by compass headings like north, south, east, and west. Those aren't numbers. Newsflash, right? Those aren't numbers, and we need to come up with a way to quantify using numbers those directions and other directions in between north, south, east, and west in order to, apply trigonometry effectively. And not just trigonometry, in fairness, there's other things. So the basic premise is this. You point yourself north and then you turn in a clockwise direction until you're pointing to where the bearing tells you to. So if it's a bearing of 30 degrees, you turn yourself clockwise 30 degrees after having been looking north. If you want to turn to the east, we know that that's 1/4 turn, so you would turn 90 degrees. Now, we need to be able to, take a look at all variety of angles. They're not necessarily going to be just north, south, east, and west. They're going to be any number of special numbers of degrees. So here's an example of one. If you're given a bearing of 72 degrees, you start drawing a north line, and I encourage my students all the time, if they start talking about bearings, start putting in a vertical line so you know where north is, and then you can estimate, or if you have a protractor handy, you can actually measure the appropriate direction. So here, B is what we call on a bearing of 72 degrees from A, and it's from the perspective of A that B is on a bearing of 72 degrees. If you were to look back from B, once you get to B and look back to where you were, you would have to add 180 degrees. Now, in mathematics, adding 180 degrees means you're basically turning exactly toward where you came from. It doesn't matter whether you turn from the left or the right, or clockwise or counterclockwise, it doesn't make a difference. And so 72 increased by 180 becomes 252. So the bearing of A from B's perspective is a 252, or a bearing of 252 degrees. You may want to pause and ask a question about that if you're not 100% sure, but basically you're looking back on the same straight line that you traveled to get from A to B. Okay, but to get started, I want to take you on a little activity that I've come up with, and it has to do with the way we understand directions at the airport. Imagine you're a pilot and you're flying into an unfamiliar airport, or you're taxiing to leave one for the very first time you've never been to. You might see these kind of signs. These are runway marker signs, these red ones that you see all over the place there. Very familiar. I'm sure you have been in an airplane and looked out the window, perhaps if you had a window seat, and you saw these signs yourself. And they provide guidance for the pilot as to where things are going. Now, these signs have everything to do with bearings, and they keep the traffic, the ground traffic, the taxiing traffic very orderly, because everybody knows where they're going. And how does all this work? What I've done is I've taken a Google Maps aerial picture of the Georgetown area, Grand Cayman, and you can see that there's the airport tucked in there. And if you do a much closer look at the airport, way down there at the ends of the runways, and again, something that you may have seen yourself from the window seat in an airplane, you'll see that runways are denoted by numbers, like this runway here, and this is straight from Google Maps. I didn't make this up. That's runway 08. And why is it runway 8? See, what they've done is they take the idea of a direction from north in terms of bearing. So if you were to approach this runway, as a lot of planes do, I've discovered, they would be landing on runway 8. What does it mean? It means the direction is nearly 80 degrees. In fact, that's the nearest angle on our compass heading, starting at 0 being at the north, and then you twist in a clockwise direction until you're facing 80 degrees. And you can see here that the 80 degree protractor heading is very nearly pointing in the same direction. If it was, beyond the 75 line going, more in a counterclockwise way, they would have called it bearing 70 or runway 7. If it were more to the east, they would call it runway 9, indicating it's a bearing of 90 degrees. So you can see that the number 08 is the nearest 10, meaning the degrees are divided by 10. And so runway 8 is 80 degrees. And that way the biggest number you're going to get is 35. If you made it all the way back up to north and it was bearing 36 or 360, you would just call it 0 again. Okay, now if you were to go to the other end of the runway, down toward the North Sound side, you would see that runway is called number 26. Well, obviously, if it's 08 one way, you have to turn 180 degrees to be pointing at a bearing roughly of 260 degrees the other way. Hence, the runway, the bearing of that one is 260, therefore we call it runway 26. And putting those two diagrams together, you can see that since runways are straight lines, obviously, I wouldn't want to be on a curved runway, the two numbers there, 08 and 26, have to be 18 apart. And why 18? Because 18 is how many, is 18 tens, 180 degrees, between those two directions, because they make up a straight line together. And this is the kind of sign that you would see along the side of the taxiways at the airport, 8/26, indicating that depending on which way you approach that runway, a pilot knows it's a bearing of 80 degrees one way or 26, 260 from the other way. Here's another airport. So I'm not just making that up. This isn't a Cayman thing. This is everywhere in the entire world. So I've chosen a major American international airport not terribly far from here, Miami International Airport. Now this airport is properly massive. They've actually got, I think, 5 runways, which is really a big deal. And I've circled the areas that I'm going to highlight. So those two magenta ones, those purpley pink ones at the top there. Then there's the blue ones, the green ones, and they cover all varieties of needs depending on the direction of the wind and how the planes want to come in, or how air traffic control wants them to come in. And I've highlighted those sections here, and you can see that those are the Google screen captures from those runways. So what I'm going to do is I'm going to bring our protractors back in here, and you can see now that the 26 and the 8, similar to Cayman, 12 and 30, and 8 and 9 and 27, they are reflective of the protractor headings, or bearing headings, or compass headings. Oh, I missed one. I didn't circle the 8 one. And they approximate, they round off to the nearest 10, take off the last digit, and that's your runway number. Okay, so let's see. Can we now put that to work? I want you to hit pause in a second and see if you can work out for yourself what runway number is at the other end that you can't see way off in the distance there. This one here is runway 14. Now hit pause, give it a think, and then come up with your answer and see if you did well. Here's another one at runway 29. Now, in this case, you can't add 18. You have to take 18 away because we're already on the higher side, right? The angle's between 180 degrees and 360 degrees, so you got to move it back the other way. Oh, watch out. Whew, that was a close call. Anyway, yeah, so you're going to get 14 plus 18 on the left side. You're going to get 29 minus 18 on the other side. Okay, now, here's a couple questions I want you to try. 3 questions, actually. You can read that for yourself. The bushwhackers, these are the old army guys that would set off and find, they would explore, reconnaissance work. And we've got a question there about they're heading off in a certain direction at a certain speed. And another guy's doing the same thing, and We got to work out where they are in relation to each other after some time. We've got this young lad here. He's going to go, oh, listen, that sounds like he's in a dangerous place. He's going to be starting an orientation course, or orienteering course, I should say. Starts at S, finishes at S, and he's going to do a triangular pathway off to A, off to B, and we'll work out all of that information using our powers of trigonometry and understanding of angles and a few other things. And the last question that we want to take a look at here, we got helicopters, we got jet fighters heading off here and there. All right, so we got a helicopter traveling on a certain bearing, got a fighter pilot heading off in a different direction, and basically we're talking about distances, times, and we're going to work out where they are in relation to each other at different times because of the speeds they were traveling and the directions they were traveling on. Okay, so I want you to hit pause right now. Oh, that's a serious pause. Car came screeching to a halt. Hit pause, and I want you to go back and try those 3 problems and see how you do. When we hit resume, I'm going to guide you through the solutions to those, but I think it's worthwhile for you to try them yourself and test your skills and see if you can apply bearing appropriately. And if you run into trouble, just let me know, and I'll be straight over to give you a hand. Okay, so here's our 3 questions again, and I'm going to go ahead and present you with the solutions to those now. Hopefully you're checking them against the work that you already did yourself. Right, so here we go. Oh, goodness me, shut up. These guys set off. Here we go. One's going on a bearing of 049. We sometimes put the 0 in front to indicate that we acknowledge that there's all 3 digits there at a speed of 5 kilometers an hour. The other one goes off at 319 at 4 kilometers an hour. How far apart are they 3 hours later? That's, So here we go. I drop a compass down, or a protractor, drop a north line down because I'm comparing to north. And what do we have? One goes on a direction of 049 and the other one goes on a direction of 319. Now, why do those numbers exist, those 41 degrees and 49 degrees? Well, the fella who went on a bearing of 49, that's pretty clear, because he started at north and he went in a direction of 49 degrees. Now the other one went on a direction of, all the way around here, 319. But I need to come up with this angle because I'm going to have a triangle here in a moment. And I take the difference between that bearing 319 and 360, which is the whole way around, and came up with 41 degrees. Now if I continue with that, I can see that these guys are in fact going to be at the opposite ends of that purple, pink, magenta line. And we need to work out how long that line is. How do we do that? Well, those last 2 angles, 41 and 49, happen coincidentally to add up to 90, which is good times indeed. The other thing I'm noticing is that these 2 speeds, 5 kilometers an hour and 4 kilometers an hour, if you travel for 3 hours, they become 12 kilometers and 15 kilometers respectively. So how do I find that? Well, yes, you could use the cosine rule because technically you have a contained angle of 90 degrees, but do you need to? This is a right angle triangle. We've got so many other options. If I want to find this distance here and I've got the other 2 and it's a 90-degree angle, I'm thinking Pythagoras. I mean, we've been dealt a good hand here. We can just take the squares of the 2 legs of the triangle. Remember, legs are the perpendicular sides of a triangle. We add their squares and it comes to 369. Does that mean this distance is 369 at the top? No. That means the square root of 369 is at the top, and it's 19.2 kilometers away. Okay, and that was given to us courtesy of our understanding of bearing. Next question was about the young man who's going for a walk. Oh, there's more noise here. So we're going to start off at S, and then A is on a direction of 56. Once we get there, we're going to stop. We're going to get our protractor back out and measure a new angle of 146. And now this is the distance is twice. Okay, too much to think about at the beginning. Let's just make a diagram here. All right, so what do we got? I'm going to say the starting point, marked by a checkered flag, double waving checkered flag here, is point S. Now, the first thing I'm going to do is I'm going to say the first checkpoint is, back with the sound, 56 degrees. Why 56? 56 is there, 56 is here, and that all makes sense. Then from there, from A, I'm now going to draw a new angle, which is 34 degrees. Why 34? Because this angle is the bearing, and that one was 146 degrees. And 146 degrees is just 34 degrees short of getting all the way down towards south, and that angle is important to us as far as the evolution of our triangle. And I think at that point we can put our protractor away, and we can work out that this young man is now at point B, and he's the blue line distance away from getting back to S. Okay, now what we haven't done is added any distance information. So what I'm going to do is I'm going to say, I don't know how far he went in the first one. They did say the distance from A to B is twice as much, and that's why I've got 2x written there. And they did tell us that B at the end was 2.6 kilometers away from the starting point. Find the length of the course overall, and I can do that. Notice again, we happen to be given a 90-degree angle here, so we didn't need any sort of high-power trigonometry. I will go to the end solve feature, but please note that 2x squared is the entire length 2x, and it's that which ultimately becomes 4x squared if you simplify it algebraically. Please don't get into the bad habit of just writing it that way, because that's not what 2x squared means. This version of 2x squared means 2 times the square of x, but actually I want the square of 2x. So this is actually not equal to each other and therefore not helpful. And you can see the calculators provide us a really handy answer of 1.16 kilometers. How far is A from S? Well, that's what x is. 2x would be twice as much. And if I continue now, it says, what's the length of the course? I've taken the previous answer here and twice the previous answer here. Why? Because it's twice. And I've added the 2.6, which is here, and that will give me the total length of the course, which is 6.09 kilometers. And the final one. This is where, watch out. Oh, okay. Fighter plane and helicopter set off from an airbase at A at the same time. The helicopter travels on a bearing of 152, and the fighter plane on a bearing of 242 at 3 times the speed. So the airplane, the jet plane, can go much quicker than the helicopter. They arrive at their bases 2 hours later. B and C are then 1,200 kilometers apart. Find the average speed of the helicopter. Lots of fantastic mathematics going on here. What am I going to do? I'm going to start by sticking a protractor down on my page. From north, I'm going to measure 152 degrees. That's 152. Hence, this is 28. And this is going to be 242. As a result, this is 62. Why do I want that? Because I want to get the angle inside the triangle. Remember, they're going to have some distance apart over here, and I need to start acquiring information inside the triangle. So that's what I've done. I'll deal with the rest of the information later on. I just want to get my diagram to be roughly correct and not confusing me. Now, I've noticed that those two angles inside added to 90 yet again, so I'm keeping you away from, troublesome trigonometry right now. I'm just dealing a lot with 90-degree angles. Now, it said that the fighter plane travels 3 times the speed of the other one. So that means distance-wise, it will get 3 times further than the helicopter would have gone. And we know that they are 1,200 kilometers apart. So this is starting to look quite a bit similar to the previous one. I've got 3x kilometers here, x kilometers there, and I can add them into Pythagorean. Remember, 3x squared is 3x in brackets squared, which would, if you were to simplify it, be 9x squared. And I can just tap that into my calculator. These brackets are essential. Without them, your calculator will spit out a meaningless number that has no help for us. It has to be 3x quantity or in brackets squared, or if you have the discipline to remember, you could just write down 9x squared there. Anyway, so that means that x is equal to 379. Now remember, that's this number here, and that's how far the helicopter pilot was able to travel in 2 hours. But that doesn't mean how fast it was going. If it travels 379 kilometers in 2 hours, then it only traveled half that in terms of speed, which is 190 if you round off to 3 significant figures. Okay, you can always